Hello students, in this video we are going to discuss 5.1, 5.2, 5.3 and 5.4 from Magnetism and Matter. A short bar magnet placed with its axis at 30 degrees with a uniform magnetic field of 0.25 Tesla experiences a torque of magnitude equal to 4.5 into 10 power minus 2 joule. What is the magnitude of the magnetic moment of the magnet? Here the given values are theta is equal to 30 degrees. That means the angle between magnetic moment and magnetic field. And magnetic field value B is equal to 0.25 Tesla and torque value tau is equal to 4.5 into 10 power minus 2 joule. What we need to find out? The magnitude of the magnetic moment we need to find out. So magnetic moment in some of the books it will be represented with small m, in some of the books it will be represented with capital M. The choice is yours. And we have tau is equal to mb sin theta, the relation between torque, magnetic moment and magnetic field. From this m is equal to tau divided by b sin theta, that is equal to 4.5 into 10 power minus 2 divided by 0.25 into sine of 30 degrees. After simplification, we will get 0.36 joule Tesla inverse or joule per Tesla. Coming to 5.2. A short bar magnet of magnetic moment M is equal to 0.32 joule per Tesla is applied in uniform magnetic field of 0.15 Tesla. The bar is free to rotate in the plane of the field, which orientation would corresponding to its stable and unstable equilibrium. What is the potential energy of the magnet in each case? Here we have two sub-questions. At which orientation the system or the magnet is under stable equilibrium and unstable equilibrium, that corresponding potential energy we need to write. Here the given data M is equal to 0.32 joule per Tesla and B is equal to 0.15 Tesla. While coming to the first part A, when the magnet will be under stable equilibrium. So the bar magnet will be in stable equilibrium when its magnetic moment is parallel to magnetic field. Your magnetic field should not be 0. That is theta is equal to 0 degrees. In this case, what is the potential energy? U is equal to minus mb cos theta, it is general expression. So u should be minimum. That is possible only if theta is 0, so cos of 0 degrees, that is equal to minus 0.32, b is 0.15, cos of 0 is 1, that is equal to minus 4.8 into 10 power minus 2 joule. Coming to part B, unstable equilibrium. The bar magnet or any magnetic dipole will be in unstable equilibrium when its magnetic moment is anti-parallel to B bar, that is theta is equal to 180 degrees. While coming to the potential energy, U is equal to minus mb cos theta. So U should be maximum for unstable equilibrium. So minus mb cos of 180 degrees, that is equal to minus 0.32 into 0.15. Cos of 180 is nothing but minus 1. Its value will be plus 4.8 into 10 power minus 2 joule. So the condition along with orientation, energy also. Energy should be minimum for stable equilibrium. Energy should be maximum for unstable equilibrium. Coming to 5.3. A closely wound solenoid of 800 turns and area of cross section 2.5 into 10 power minus 4 meter square carries current of 3 ampere. Explain the sense in which the solenoid acts like bar magnet. What is its associated magnetic moment? Here two sub-questions are there. First of all, the given values here, the number of turns are 800 and area of the cross section A is equal to 2.5 into 10 power minus 4 meter square and the current value is 3 ampere. The first sub-question is explain the sense in which the solenoid acts like bar magnet. We are aware of bar magnet. Suppose say this is the bar magnet and the magnetic field lines will be look like this. They will start from North Pole outside. They will enter South Pole, but inside they will move from South Pole to North Pole. Similarly, if we are taking a solenoid, assume that These are the turns. The current I. Suppose say here it is coming out, here it is entering, the current is coming out, here entering. That means if you observe with the help of right hand thumb rule, so the magnetic field will be like this, and outside that can be formed like this. And if you observe inside, the direction of the magnetic field is from left to right. That means this end will be acting as like south polarity, the other end will be acting as like north polarity. That means, but actually we will take the magnetic field outside of the solenoid is negligible. If you observe these two diagrams clearly, the magnetic fields, the magnetic field of a solenoid has the same pattern as that of a bar magnet. It acts along the axis of the solenoid. Its direction is determined by the sense of flow of current. Here I have taken the current such a way that it is like this. If the direction of the current is varied, the direction of the magnetic field also varies. This is one subpart. While coming to one more subpart, what is its associated magnetic moment? Now, the magnetic moment M is equal to NIA. N is 800 and I value is 3 ampere and A value is 2.5 into 10 power minus 4, that is equal to 0.60 joule per Tesla. Coming to (5.4). If the solenoid in exercise 5.3 is free to turn about the vertical direction and a uniform horizontal magnetic field of 0.25 Tesla is applied, what is the magnitude of the torque on the solenoid when its axis makes an angle 30 degrees with the direction of the applied field? Here, the given data is the magnetic moment is equal to 0.6 joule per Tesla. What is this value? This value we got it in the previous problem. Magnetic moment. This is linked with previous problem. And B value is equal to 0.25 Tesla and theta is equal to 30 degrees. Therefore, torque acting on the solenoid tau is equal to mb sin theta, that is equal to 0.6 into 0.25 into sine of 30 degrees, that is equal to 7.5 into 10 power minus 2 joule. So these are the solutions from 5.1 to 5.4. If you feel these concepts and solutions are helpful for you, please kindly subscribe and share. Thank you.